Alright, so now we're going to talk about heat and phase changes. In all honesty, it's mostly phase changes, but heat causes phase changes, so they're paired together. So, heat and phase transitions, right? We've talked about how temperature relates to the motion of gas and molecules, but temperature changes can also cause matter to change state, right? It can go from a solid to a liquid, or from a liquid to a gas. And understanding how energy drives these phase transitions is essential in really all sciences. So, internal energy, right? We derived an equation for the internal energy, and we briefly talked about how molecules move about in random directions, right, from a using random walks in Brownian motion. So this random microscopic kinetic energy is part of what we call the internal energy of the system, right? So the internal energy of a system is just the total energy of all of the molecules in the system, except for the macroscopic kinetic energy, right? Kinetic energy that's associated with macroscopic translation or rotation. Think about like the translation or rotation of the entire system, not just the individual particles. So, we need to talk about what is a system, right? So a system is whatever we define our system to be, right? It could be one object, like with forces, or it could be a group of objects, like when we're thinking about kinetic energy and potential energy and energy conservation, right? So everything that is not a part of our defined system that we defined is considered to be external to the system, or the surroundings of the system. So internal energy includes translational and rotational kinetic energy of the molecules, and this has to be due to their individual random motions. It also includes vibrational energy, right? So the vibrational energy of molecules and atoms, and potential energy due to interactions between the atoms and molecules of the system. Internal energy also can include chemical and nuclear energy. We're not really going to talk about that, though, in this class. Internal energy does not include the kinetic energy of the molecules due to the translation, rotation, or vibration of the whole system. It also does not include potential energy due to interactions of the molecules of the system with something outside of the system. So, like gravitational field. And heat, right, we've already defined, but heat is just the energy in transit between two objects or systems due to a temperature difference between them. So, temperature measures the molecule's average kinetic energy. Internal energy is the total energy of all the molecules, and heat is the transfer of energy due to differences in temperature. So, heat and work are similar in that they both describe a particular kind of energy transfer, right? Work is energy transfer due to a force acting through displacement of an object, and heat is a microscopic form of energy transfer that involves large numbers of particles, and the exchange of energy occurs due to the individual interactions of those particles. So, no macroscopic displacement occurs when heat flows, and no macroscopic force is exerted on one by the other. So a system can possess something like energy in various forms, including the internal energy, right? A system can possess kinetic energy, a system can possess potential energy, but a system cannot possess heat or work, right? Heat and work are just two different ways of transferring energy from one system to another. And it's important to remember the direction of heat flow, right? So heat flows spontaneously from a system at higher temperature to one at lower temperature, meaning heat flows from hot things to cold things. So if we want to discuss how heat and a change in temperature are related to each other, we need to talk about something called the heat capacity, right? So the heat capacity is equal to, the heat capacity is the C, is equal to heat, Q, divided by the change in temperature, meaning that we can determine how much the temperature is going to change of an object based on how much heat is applied and that object's heat capacity. And heat capacity is specific to objects, right? So certain materials have certain heat capacities. So the heat capacity of water in a drinking glass is actually going to be much smaller than the heat capacity of water in Lake Superior. That's because there is an involvement of mass. And when we think about how mass is involved in the change of temperature, we are thinking about something called the specific heat capacity, or sometimes we just use specific heat. So heat capacity, capital C, specific heat capacity, lowercase c. And this specific heat capacity, or just the specific heat, involves the mass of the object. And that makes sense, right? If I apply some amount of heat to an object, and there is, well, let's say I have two objects. They're both cups of water, but one is literally 8 ounces of water, and one is like a gallon of water. I am going to have different changes in temperature if I apply the same amount of heat to both of these. Why? Because there is more mass of water in my gallon than there is in my 8 ounces. So, the amount of heat needed to raise an object's temperature is determined by the material's specific heat or specific heat capacity. We can also talk about the specific heat of ideal gases. So the total translational energy of a gas containing n number of molecules, or n moles, is defined here. And in our last lecture, we derived this entire thing, right? But there's a little bit of a catch here. And this specific equation is only valid for a monatomic gas, right? Because all of the requirements and assumptions that we made for this derivation required us to have one type of atom, and all the atoms had to be exactly the same, right? A monatomic gas. So the specific heat with a constant volume is going to be equal to 3/2 N, right? This is how much energy we need to change the temp 1 degree Kelvin. So this 3/2 R is our specific heat variable in our internal energy equation. So for a monatomic gas, it's 3/2 R, but for a diatomic gas, it is 5/2 R. So why are these fractions different? Well, monatomic gases can store energy as essentially translational motion, right? This object, right, if you imagine a billiard ball or like a tennis ball, no, a tennis ball isn't good because it has lines on it. Imagine that you have a bouncy ball that is solid in color. And I take this bouncy ball, I can translate it in left and right, up and down, forwards and backwards, and all of these are going to produce different internal energies. Why? Because I have translated the object, I've changed its position, things like this. If I hold my bouncy ball in one location and I spin it about its axis, because this thing is symmetric and the same everywhere, this is not going to change the internal energy of the system. Now, if I switch that out for something like a baton or a stick with 2 balls at the end, and these balls are different sizes, right? I can still translate it forwards, backwards, up, down, left, right, but I can also spin it. And as I spin it, right, I no longer have this symmetry involved. And so this is an additional 2 directions of motion. This adds and gives me 5 potential ways to store energy. X, Y, Z direction, as well as 2 directions of rotation. So for a diatomic gas, my 3 turns into a 5. Also, molecules can store energy in the vibration of their atoms. So you can imagine a water molecule. Those bonds can flex, and they can like pump back and forth. I'll do a demonstration in class, don't worry. There's hand gestures with this. Those are also additional ways that you can store internal energy. Oh, look, I made a picture. Yeah, so translational, X, Y, and Z. There's my baton with 2 little balls at the end, right? So I can translate it left, right, up, down, back, forwards, but I can also spin it. And as I spin it, I'm going to be changing the energy of the system, right? I'm changing the potential. I'm changing the system's positionality. So with something like an H2O molecule, we can have translational. I can move it left, right, up, down, back, forwards. I can spin it along axes, but it will also vibrate. So these bonds can move back and forth, they can kind of flex up and down, and these are also ways that internal energy can be stored. So each one of these 3 halves, these 5 halves, these are ways of storing energy. They are also called degrees of freedom. If you would like to learn more about why it is 1/2 R for each degree of freedom, you can look into the equipartition theorem. So this is an example of the 3 of translation and the 2 of rotation, right? If I spin it along the x-axis, there's going to be no change, right? It's fairly symmetric. I'm not going to visually see any difference. If I spin it around the b-axis and the z-axis, right, there are going to be differences here. So if we want to talk about a phase change, right, taking something from a solid to a liquid or a liquid to a gas, in addition to needing to understand the heat capacity, I also need to understand something called latent heat. And latent heat is the energy that's required for a material to change its phase, right? So we have here like a diagram of a phase change, right? So if I have ice, if I add heat, is going to increase the temperature, increase the temperature until I hit 0 degrees Celsius. And then something happens, right, where this flat line occurs. And this flat line is energy that is going into the system specifically related to phase changes. So in this situation, it would be breaking the bonds between the water molecules so that instead of a solid ice, I can have water. And then, same thing here. Then I will be breaking the bonds to create steam and then heating up my steam. So, when we have a phase transition, we have a substance changing from one form to another, and we can represent that as the heat is equal to the mass of our object times the latent heat. So, Q is our heat of transformation, right? It's just the amount of thermal energy that we are putting into the substance. Mass is the mass of the object, and latent heat is going to be the energy that is either absorbed or released by a substance during this phase change. And remember that these phase changes occur without a temperature change. So, there are 3 different forms of latent heat. There's the latent heat of fusion, which is either melting or freezing, the latent heat of vaporization, which is either boiling or condensation, and the latent heat of sublimation, which is either sublimation or deposition. And both of these, all 3 of these, are going to have a positive or a negative value, right? So, going from a liquid to a solid, I am going to be losing heat. Going from a solid to a liquid, I am going to be gaining heat, right? Freezing, losing heat, melting, gaining heat. Both of these are heat of fusion. One is going to be moving in a positive direction, one is going to be moving in a negative direction, right? Adding energy or releasing energy. So, when a substance is in a solid form, bonds between the atoms or molecules hold them in almost fixed equilibrium positions. Energy has to be supplied to break the bonds and change the solid into a liquid or a liquid into a gas. So when a substance is changed from a liquid to a gas, energy is going to be used to separate the molecules from the loose bonds that hold them together and to move those molecules apart. So the temperature doesn't change during these phase transitions because the kinetic energy of the molecules is not actually changing. Instead, the potential energy of the molecules changes as work is done against the forces that are holding them together. Because our kinetic energy is not changing, our temperature is not changing. Instead, this energy of heat that is being supplied is going into changing the potential energy of the system. So, there are different methods of heat transfer. Conduction occurs when objects are touching. Convection is going to be heat moving through a fluid. So, remember that fluids are also gases, so like your air fryer is a convection oven, just renamed as an air fryer, it's just a convection oven. And then radiation is heat that is transferred through electromagnetic waves, and you'll talk about that in the second semester of this class. So, heat flow with multiple objects. Let's suppose we have some water and it's heated in a large iron pot by dropping a hot piece of copper into the pot. we can define the system that we're looking at to be the water, the copper, and the iron pot. The environment is the room containing the system, right? So everything except for the water, the copper, and the iron pot is considered the environment. So heat continues to flow among these three substances until they reach thermal equilibrium. So I need to add up the heat due to the copper, the heat due to the iron pot, and also the heat of the water. We also are going to have to determine when heat is positive or negative. If you are gaining heat, it's positive. If you're losing heat, it's negative, right? So an endothermic process is a process that absorbs energy, so heat must be added, and Q is positive. This would be things like melting and boiling. Exothermic, right? We are releasing energy. Energy released is going to be negative. Our heat is going to be a negative value, and this would be things like freezing and condensation, right? We have to lose kinetic energy in order for our molecules to freeze together into a solid object. So, thermal conduction is the transfer of heat through a material via direct contact. So this happens when faster moving hot particles collide with the slower moving cool ones. Isn't it interesting, like whenever we think about heat transfer, we think about like, oh, this is something we can't see, like there's heat, but I don't actually like really see heat, but like it's just particles colliding with each other. I mean, if you really like sit and think about it for a while, it's super fascinating. So we can imagine this flow. We can imagine these collisions as the flow of heat from hot areas to cool areas, right? So when we're thinking about something like thermal conduction or heat transferring from a heat bath to a cool bath through something like a uniform rod, we use this following equation. And K in this equation is going to be our thermal conductivity. And I think it's really important to note that our temperature subscripts in the numerator are hot and cold. They are not initial and final. This is not delta T. This is hot minus cold. And it is always going to be hot minus cold.